I'd like to welcome you to Unit 1 of Thinking Like an Engineer. And in this unit, what we're going to do is we're going to focus on identifying the problem that you wish to solve and also coming up with a design that you wish to pursue that you can actually turn in about a week as your initial design so that I can take a look at it and see where you are and the kind of things that you wish to do in your school environment. So by now, hopefully you've got a chance to read the first assignment. It's from the Engineering in K-12 Education report from the National Research Council. If you haven't read it, not a problem, but just hang along there with us, and I recommend taking a look at pages 4 through 6 and 27 through 48 to give you a sense of what it is I'm going to talk about today. We're going to start first of all with problem solving. And problem solving is often looked at as a search of possible solutions in an array or sea of alternatives. And what it also means is finding your way through various different kinds of situations, evaluating where you are in that what's called that search space, and trying to get a sense of making your way towards a goal. So you may find yourself at anywhere in the search space. You may find yourself in the beginning of that search space and seeing the whole process ahead of you. You might find yourself within that whole problem, within that search space, and trying to figure out how you got there and how you're going to get out or where you're going to go in that space. But everywhere you are in that space, you're making decisions. You're looking at various kinds of alternatives. And many people look at problem solving as the process of looking through a space of alternatives where you're looking at trying to search through that space. So that's what we want to actually take a look at right now, is that we want to look at K-12 engineering as a kind of problem, as a kind of issue, something that we want to try to address in a certain kind of way. And in this class, in this course, we have about 3 different kinds of design alternatives to help us negotiate that space, if you will. And if you ever wondered about problem solving and why I haven't necessarily given you some very specific problem solving kinds of strategies or ideas, let me just ask you to do the following. Go in your favorite search browser and actually type in the term problem solving and actually look through that and Google it, if you will. Take a look at all the various different ways in which people see how problems can be solved. What I do very often is I take a term, and instead of looking at it from the standpoint of text, I look at it from the standpoint of images. So I use Google in this case, I look through and find all the images associated with problem solving. And if you do the same thing right now or even a little later, what you're going to find is that there are a lot of different ways in which people say problems can or should be solved. So what that means to me is that what we have to do, what you have to do, is to identify and be aware of and reflect upon your own problem-solving strategy. Very often that problem-solving strategy can be driven by what's going on in the situation you're in. It could be various other kinds of things, but what I recommend right now is to come to grips with your own problem-solving strategy. And it's not necessarily a strategy that you'll have to, let's say, identify. It won't have a name to it necessarily, but you'll have a sense of how you operate in unknown circumstances where you maybe don't know what to do, and you're trying to gather and figure out how to proceed in this space. In other words, have you entered the space yet that you're getting ready to solve? Are you in the space of the problem you're getting ready to solve? Or, for example, are you find yourself in the midst of that, as I mentioned earlier? Or have you negotiated successfully in that space and actually now looking for other places in that space where there are other ways to address the problem, if you will. And we'll get to that point a little bit later. So take a look at those, if you will. You can stop the video right now, take a look on your own, get a sense of what's out there in terms of how people recommend doing problem solving, and then come back to the video, or else you can do it briefly while we're moving on to the next topic. But nevertheless, I recommend that you do that. And throughout this particular course, and particularly throughout this unit, I'll ask you to do that. So problem solving is searching through the space of alternatives. What's interesting about science versus engineering, if you will, or science and engineering, is that science is often addressed as a set of disciplines that look at phenomena in nature, if you will. So when you're looking at chemistry, chemical reactions, looking at biology, how life progresses and works across various species, physics, how things move, if you will, and other kinds of sciences, it's looking at phenomena, if you will, and looking at observations. And if you do the same thing with scientific method, if you will, as I asked you to do with problem solving, you'll find a lot of different ways in which the scientific method is actually brought to bear. Why am I talking about science now? Because I think science and engineering are kind of two sides of a very same coin. In science, we look at phenomena. various phenomena in terms of nature, as I said before, and in particular, out of the scientific methods, we look at observations. Out of all the different steps, I want to focus on three. We look at observations, we come up with hypotheses, and we create experiments, right? But in engineering, we're solving problems. And when we think about problem solving, it is actually from the perspective of a person or people in which problems can be solved. So engineering looks at people, problem solving, and science looks at nature and phenomena. Same concept, same idea in a way, and with various rigorous ways of actually going about doing it. So in this class, thinking like an engineer, we can also depart a little bit if we think of ourselves as a kind of a scientist of problems, where we can actually look at various ways in which engineering can help us solve those particular problems. So let's move forward and take a look at how we might move and understand that, but let's make one thing, make one step first before we do that. We know that not everyone is an engineer because not everyone has actually studied and learned how to integrate science and mathematics or figure out how to use both of them to actually solve problems. And so very often, even in the messaging around engineering, science and mathematics is clearly part of what we want to suggest. However, William Wolff, who was the past president of the National Academy of Engineering, said once, in a writing, he mentioned that he operationalizes engineering, he can at least, by looking at engineering as design under constraint. So while deep mathematics knowledge, deep science knowledge isn't always necessary to solve problems, if we actually now start to generalize and relax the constraint on engineering as being the application of math and science to something a little bit more broad as design under constraint, then we can now start to cast the net more widely to get people to understand some of the principles and ideas behind engineering, especially when it's related to making sure that engineering is diffused into various kinds of educational activities in the K-12 sector. So let's take a look at that. And for the remainder of this unit in this course, we're going to see engineering, or posit that engineering is designed under constraint. So we'll use Bill Wolff's ideas, move forward, and take a look at ways in which we can now start to see engineering from our own perspective based on where we are and what it is we want to do and what problem we're trying to solve. We're still moving towards that problem we want to solve. Will allow us to take a little time to get there, and bear with me, and we'll find our way to identifying that problem, especially when we start to look at designs. But before we get there, we want to actually focus on two different kinds of things. One thing is that we want to focus on within the scope of problems is what's called a closed-end problem. A closed-ended problem is a problem that has one solution. One solution all by itself. You see this sometimes in mathematics where we do an equation, x plus 4 equals 7, that generally has one solution, if you will, to it, and you can start to play around with the notion of x and things of that sort, but there's one solution we're looking at. However, an open-ended problem is one that has multiple solutions. And often, in engineering, there is not just one solution to a problem. And in fact, often in life, there's not always one solution to a problem. So in some sense, if we again use the fact that engineering is designed under constraint, we can clearly see that we've all solved problems in quote-unquote an engineering kind of way without necessarily having, again, deep mathematics and science, but we've been able to take and understand how to solve problems. We want to bring that experience in solving problems to this particular unit and to this class and use it to help design and figure out what it is we want to do within the context of what we want to try to achieve. So that moves us to the next section of our unit, which is looking at designs. Designs I'd like to ask you to consider, one of the designs I'd like to consider, is based on your experience. And we'll go through each design. I'll give you a sense of the kind of experience that I hope that you would have and to bring to bear when indeed we want to try to figure out what designs we want to try to achieve. Lock in your mind the kind of problem you think you're trying to solve. We'll take a look at designs, and then we'll go back and forth, if you will, to try to take a look at the problem and the design to see if we can now start to converge upon a pair that works for you. One, depending on your experience, if you have, for example, no experience in K-12 engineering, really are interested in trying to figure out how to integrate it, and don't know necessarily quite what to do right now, then I recommend that you consider building a multimedia portfolio. A portfolio of text, images, video, audio, possibly animation, for two reasons. One, it will build your idea of literacy, in terms of enhancing multimedia literacy, which is a really great skill for any educator or program director or anyone involved in what we do to have a sense of. Many of you may already have multimedia literacy skills, that's fine. Enhance them, revisit them, bring them to bear in what we're trying to do here. And I think that's one way to do that. So one of the products, if you will, that you can create in this particular course is to create this multimedia archive, if you will, a portfolio of resources. Well, you say, well, why don't you give us some of those resources? What do you think is actually necessary for us to know as around K-12 engineering? Certainly I could do that, but what I'd rather have you do is to actually start to really engage in the engineering problem-solving process. Often, when a problem is solved in engineering, there are no textbooks, there are no resources per se. One has to identify them all, build them, collect them, make decisions, what's in, what's out, and figure out how to do that. Now, for this particular type of design, one of the things you might want to put yourself in touch with is what kind of learner are you and what you want to do with the design. Is it designed for you? Is it designed for other people? What do you want to do with the design? So I'm assuming right now, and this is where you can help me, I'm assuming that you're interested in K-12 engineering, and you're interested in it for yourself. So if that's the case, one of the things you may wish to do, and I advocate you doing this, is go off to the web and look for various kinds of tests of what kind of learner you are. If you are a visual learner, auditory learner, kinesthetic learner, or let's say a textual learner, someone who deals with reading and writing, and actually for that kind of learning with reading and writing, that works best for you. So get a sense of what kind of learner you are, and that may help guide you as to what type of design you wish to create, what type of portfolio you wish to create. Is going to be heavy on audio, heavy on video, for example, with a few reading kind of assignments, or what combination of text, image, video, audio, and animation would you be willing to try to put together for that? That's one design that you can consider. And it requires you to do a little bit of work for yourself, but nevertheless very important that you try to take a look at what it is you're trying to solve, who you are, and how you relate to that problem. 2, if you have some insight on, for example, on how, or teaching responsibilities, for example, that you may want to enhance by looking at K-12 engineering, then one recommendation, the second design you could consider, is creating what's called a lesson, unit, or program plan, if you will. That may be project-based or inquiry-based as a result of this particular kind of effort in this course. It could be one that you've created, it could be one that a lesson plan, a learning plan, or program plan that you found online that you wish to customize. You wish to maybe surgically take K-12 engineering and put that into your particular plan and focus on it. Maybe it's a favorite lesson that you have that can be enhanced, or you wish to enhance in a certain kind of way. So one thing you could do, if you have that insight, have a sense already, you may want to create a lesson plan, a learning plan, or program plan. I say program plan because many individuals here might decide to be part of after-school programs and want a routine or some kind of path that they can take their students or learners through. And so it may resemble a lesson, but it may focus on a particular program to maybe satisfy some funding constraints or anything like that. So a school or community kinds of foci, then you could also do that. So consider that. And also, if need be, I recommend the 5E learning cycle. The 5E learning cycle, for those who don't know, have 5 distinct phases: engage, explore, explain, elaborate, and evaluate. And I have a template for that in the toolbox. You can take a look at that to see if it helps you get a sense of this type of design and what you might want to create here. The last design is for those who have a vision for K-12 engineering, and that vision now starts to be larger than them. So what I'm also suggesting is that the third type of design is a proposal to an individual, a proposal to a department, school, organization, or even funder that actually embraces the idea of K-12 engineering. And so if you are indeed envisioning yourself as an advocate and want to strengthen your position politically, socially, intellectually, professionally in a given certain environment, a proposal might be the right thing for you to try to create. So I'm willing to take a look at proposals, I'm willing to take a look at lesson plans, unit plans, I'm willing to take a look at portfolios and resources and help integrate those resources for any one of you. So I recommend, as part of this course, choosing one of those 3 different kinds of designs and not try to figure out, I think this is what's really good for me. Now, Associated with that is also looking at the problem that you intend to solve. So what is that particular problem? Is it something that's related to a curriculum? Is it related to something that a school is adopting, maybe a charter school, for example, that's looking for some type of direction or some type of aspect of their science or mathematics or STEM curriculum, if you will, that might be useful to you. So again, looking at the design, finding out who you are and what resources are available to you, what you wish to try to achieve, and what problem you're trying to solve is actually an important piece. So the point of the first lesson, this first course, if you will, a unit in this mini course, is to actually identify that problem. What is it that you wish to do? How do you wish to do it? And use engineering type ideas to do that. So let's go up forth a little bit more to talk about our design resources and to kind of see design features, I should say, to get a sense of how we might take a look at solving this problem. Now, if you look back just briefly at what I mentioned about this idea of problem and design, you'll notice that I suggested that there is some type of iteration between them. And iteration is one of the design features, and you'll see that outlined clearly in the reading. There's this process in engineering, and in problem solving in general, I think, but particularly in engineering, of going back and forth between problem and design. What is it that we're trying to solve? Remember, science looks at phenomena, engineering looks at problems. What is the problem? For example, if you're dealing with a problem independently, you may find that others who are looking at or dealing with the same problem might look at the problem from a very different perspective. In fact, they might even see a different problem than you see. So, in engineering, one has to find some type of collective agreement or some type of way to come together to say this is indeed a problem that needs to be solved, or this is a problem that I think I should solve. Sometimes you may reach out to find others who are participating with you, or others who might be used as sounding boards, or others to brainstorm with, to figure out, am I really seeing the problem for what it is? Do I really see what I see? And if you notice the analogy, and I'll use this throughout the course on science, then when you look up in the sky and you see a phenomenon, or you see some type of phenomena in terms of physics or some type of atomic phenomena or biological phenomena, sometimes it really helps to have another person there with you, or share what you see, what your observations are with others, in order to get a sense of whether or not you're seeing the problem the way you think you are. And so you find these little slight, what are called perturbations, or slight incorrections, if you will, or updates to how you may actually be viewing the problem. So again, we're starting here in this unit of strictly seeing how we can solve problems. So there's this iterative process of refinement, redesign, rethinking, and then you'll also find yourself, when you do that, in what's called a design cycle. Again, as I will mention throughout this unit, and possibly in some other units, go and search on the web for the term design cycle and look at it from the perspective of images, not just text, but images. And when you do that, if you're doing it right now, for example, you'll see a plethora of different kinds of drawings and ideas for how images that represent what it means to be involved in this design cycle. So like I said before, the process we're going through is an engineering process, because you must decide, out of all those different ways of doing things, decide for you what that iterative process really is, how indeed you can see where you are in a design cycle. And right now we're going to stick with the simplest of the iterations between two things. One is a design, and two is a problem. So I'm going to ask you to revisit that once again. What is that problem indeed you're trying to solve? What is it that you want to try to accomplish? And again, what design works for you? So this also means being very honest and transparent about your own experience and saying, okay, I really don't know a heck of a lot about K-12 engineering, so I'm going to use this as an opportunity to learn. In a short amount of time in this course, as part of the HP Catalyst Academy, what we want to be able to do is to see how we can solve this particular problem I have. I want to get into this game. I want to see what it's like. So I'm going to go out and find things, and I'm going to use me, the instructor of the course, to bounce those ideas off of, to get a sense of where it is I am. Try to share with him what problem I'm trying to solve. So as we go through this day and during the next, between now and the next time you actually see the next piece for the next video for this course, you want to be able to refine and iteratively go through the process of looking at that problem and seeing what design works for you. Some of you may decide to take this leap of faith and say, I don't really know a lot about the K-12 engineering world, but I really want to create a lesson plan for it. I learn best by creating something I'm really going to use, and that's the way I want to start to get involved. You know the type of learner you are. In some sense, you're kind of kinesthetic, you're hands-on. You want to build something on your own to kind of make it work for you. Then even though you don't have a lot of experience, then a lesson or unit plan might be something that works for you as well. A unit plan might be too many lessons, 3, 4 to 5 lessons maybe. I don't want to create that many, but I might just focus on one lesson to see how I might do it. And I might use my favorite strategy, if it's 5E or some other strategy, to make ends meet and create this artifact, create this design that I can use going forward when the course is over. Okay, so iteration, refinement, redesign, being involved in the design cycle, and as part of problem solving, choosing among a large set of alternatives that you might have in order to try to achieve something, to make sense out of the many, many, many things, to either identify a few or one or two that you might use going forward to create what you need to create. Solutions. You noticed earlier in the video I talked about closed-end and open-end solutions. Open-ended solutions, again, are solutions, open-ended problems, I should say, have many different kinds of solutions. Closed-end problems have one type of solution. So, what we want to be aware of and make sure that we are not just aware, but able to accept is the fact that when we look for our designs, we may have many, many, many different solutions. So, if you look at the problem of creating a portfolio, or creating a lesson plan of some type, or creating a proposal, you can now see that there are many different types of proposals, many different types of plans, many different types of portfolios that one could create. How do we decide which one works for us? What makes sense to us? How do we now start to take that and bring it down, understanding that there are many, many, many different ways of doing business like that. So a short story is I remember in undergraduate school as an engineering student that I remember our teaching assistant putting a transistor in a device and showing us the transistor being powered by being powered and showing an oscilloscope trace of the transistor. And so there were several curves on that particular trace, showing how the transistor was being used in multiple ways to amplify a signal, if you will. And I asked him, well, what was all those different those curves? He said, well, that's a family of solutions, he said, to the transistor, a family of different ways in which a transistor can be driven to amplify in a given set of circumstances in the circuit. That story stuck with me, as you can see, and reminds me that when you see a situation and looking at a problem, there may be more than one solution. And you can see and remember situations that you know, where you get stuck. You say, you know what, I've got to solve it this way. There's no other way around it. I don't know why I'm looking at anything else. I don't know why others are telling me that those other people are wrong, so forth and so on. If we step back a little bit, open our mind and our thinking, and realize that there are many different ways in which we can now start to solve any given problem, then we start to maybe open ourselves up to seeing these various alternatives. So what we now know that if we have or think there not only are multiple solutions, but we now start to dig a little bit deeper and looking at what are called the constraints. What are the constraints on the solutions? In other words, so there may be 100 different ways of solving a problem, but the constraints only point to the fact that 10 of them make sense from a lot of different perspectives, in terms of resources, time and money, in terms of our understanding, or other kinds of factors, if you will. And so what the constraints do is start to make the design reflect a certain set of specifications. So in other words, the problem demands the design to have a certain kind of look and feel, if you will, and then the number of constraints that you have, if you will, of the problem start to interact. So constraints and specifications work on the design part that should reflect a really true and valuable solution to the actual problem. And so now that is steeped in what's called decision making. So you, the designer, you, the engineer, are really now start to make sense of what is this design, what is this situation, what is this decision making that I really need to accomplish in order to make this design something I can actually build and test to see whether or not indeed it does work. So we want to make sure we look at those design features, iteration, back and forth, and also solutions and a wide class and variety of solutions to make this work. Again, what makes engineering distinct as a discipline, or a set of disciplines, if you will, is the fact that very often the solutions require an understanding of mathematics and science. And accordingly, there's also a necessity to have some type of technology often to really solve those problems. So while not all problems require mathematics and science in an explicit way to solve, the kind of general problem-solving strategy using design under constraint and bringing these pieces together are really a true and authentic kind of engineering experience. And this is what we're advocating for here in this first unit and throughout the course. We want to actually close to our video today by looking at various things that can inform that process of that design under constraint process, if you will. And as part of your package of readings, take a look at the Next Generation Science Standards. You'll notice there are no standalone engineering standards in the Next Generation Science Standards. And you'll notice there are also no engineering standards in the Common Core Standards as well, which are math and science, math and language arts, if you will, right now. There aren't enough. It had been looked at, if you look at online at the National Research Council, the National Academy Press, for a report, and the report will suggest that some experts took a look at whether or not engineering standards made sense all by themselves, and they didn't. The infrastructure for doing engineering in K-12 just doesn't exist. Having a set of national standards for that all alone, in their judgment, it wasn't the right thing to do at that time. So the emergence of the Next Generation Science Standards and the science and engineering practices, as well as the K2, the 3-5, middle school and high school engineering standards, now are available to us in the context of the science that we've known has been in schools for decades and decades. So we can now use that as a foundation, use that as a launching pad for looking at how we may look and craft K-12 engineering. I recommend that now or sometime later, take a look, if you haven't already done so, take a look at those standards. Take a look at how the science and engineering practices are threaded throughout the entire set of standards. Take a look at the specific K2, 3-5 middle and high school engineering standards and what they're asking students to do, what is required of teachers or educators, program developers, you name it, to do, curriculum experts, and take a look at where you are in that mix of different kinds of understandings. Take and also remember that in solving this problem in an engineering type of way, it's very important to bring in bodies of knowledge that help inform that process. In engineering, as we understand it, those bodies of knowledge come from science, they come from various types of mathematical tools, and increasingly, and also in computational kinds of tools to help us solve those problems. Well, the standards are tools. They're directions. They give us some insight as to what it is we need to do to make sure that the work that we're doing in K-12 engineering meets those standards, interfaces with science, and increasingly is integrative across the curriculum. So take a look at those kinds of standards so that they can actually help inform that decision-making process. And I recommend two last things. One, take a look at project-based learning. Project-based learning is the use of real-world situations and environments to help bolster an understanding in a given classroom situation. It doesn't have to be done in engineering, but for this particular class, looking at engineering, I recommend taking a look at project-based learning. And you'll find with project-based learning that even in engineering schools, they're realizing that project-based learning is something that is important to include and strengthen in the curriculum. So you can see that there's this interesting duality, this interesting marriage, if you will, of project-based learning and engineering, and there's a lot to be learned from each other. Yes, engineering is not project-based learning, and project-based learning is not engineering, but there certainly is overlap. And that overlap is something that we're going to find, especially in the next unit when we discuss STEM interconnectedness. How to look at that overlap is going to be critical to how we actually see and start to solve problems. Lastly, take a look at inquiry-based learning. Take a look at it, I recommend, from one perspective. One, what is the knowledge it takes to really ask questions? How do you motivate and set up the conditions for students or someone who is actually looking at phenomena, or in this particular case, as someone who's looking at solving a problem? How can they actually now start to engage in that process, and what do you need to actually do that, and what do you need to have in terms of scaffolding for someone to be actually be able to take advantage of a situation in learning, to pull all that together, and how can you guide them in order to accomplish this process. So string these ideas together for this particular first unit. I think we'll have a good understanding of where we are. So please reach out, take a look at the problem you're trying to solve, the design you actually wish to try to have and to use to solve that problem, and that will be your basis for your initial design. So between now and the next time we complete or take a look at our work through this course for the next unit, what we want to do is we want to decide on that problem, decide on that design, and then move forward to try to build, if you will, a design that actually helps to solve that problem. So we'll come up with what's called an initial design. I thank you for your attention. I appreciate it, and I'll see you in the next unit.